All right, so I'm going to take you through one of the rolling without slipping problems that I showed in the sim. So essentially this idea is that you're going to have an object that is not meeting the non-slip conditions. So it's either skidding and then it begins to roll without slipping, or it's spinning its wheels in place and then finally starts to roll without slipping. So we'll do the one that was in the sim that I showed a little bit earlier today. This is where it has some initial translational velocity in this direction, and we'll call that the positive direction, but its angular velocity initially is equal to 0. So this thing is going to move along, and if we look at the free body diagram, okay, it's sliding along. It's going to have kinetic friction that it's going to act opposite to that motion. It's going to have a weight vector, and then it's going to have a normal force. I'll just put an N there. And we know these two are going to be equal because it's in translational equilibrium this direction. So this frictional force is not only decreasing the linear speed, because it's opposing that linear motion, it's also going to act as a torque to increase this angular velocity here, so that while both of these things are going, eventually our rotating object will get to this point where it's rolling without slipping, and then it meets that condition right there. So typically the problem is asking, how much time does it take to begin to roll without slipping, or over what distance does it travel until it starts to roll without slipping? So we have to deal with this half of the problem without looking at that. So what do we want to do? We want to go back to tried and true laws, Newton's second law. So I'm going to start with the linear motion first. So if I look at the net force acting on my object is equal to the mass times the acceleration. My net force in this case is going to be friction. It's slowing, causing it to slow down, so I'm going to have a negative sign in front there. And then I'm going to have m times a, step 2. All right, friction is defined because kinetic friction is always equal to mu times the normal force. Remember, static friction is the one that's less than or equal to. And in this case, we know our normal force is equal to our weight, so we can substitute in mu times m times g is equal to m times a, and we get a expression for the linear acceleration of the object. And one of the things that we notice right away is that this is a constant. So this automatically is going to give us permission to use our kinematic equations, the big four that we're used to. If I need to solve for the velocity as a function of time, I could certainly integrate both sides, but I don't really need to, because since I know that it's constant acceleration. So slide over here a little bit. So if I want to find an expression for the velocity as a function of time for this ball as it begins to go from translating to rolling without slipping, I know it's going to have an initial velocity v naught that's given, plus, but in this case it's a minus sign, my acceleration, which is mu times g times t. So we have this expression for the velocity as it gets to the point where it begins to roll without slipping. But what we don't know is at what time does this happen. So if I want to figure out at what time does this happen, I can use Newton's second law, but for rotational motion, and get an expression for the angular velocity. And then the time at which it begins to roll without slipping is when I can meet the magical condition v equals r omega. So that's the next step in our puzzle that we're trying to get to. So we're going to go through finding this expression for omega. So now I'm going to use rotational Newton's second law. My net torque is going to be positive Fk times r, because this is acting as a torque to increase the angular acceleration. My moment of inertia, I'm just going to put in a shape factor k mr squared, and then I'm just going to leave alpha. Remember, we can't use the non-slip condition yet. We have to just leave it as the angular acceleration. We can do some simple cancellations here. One of the r's are going to cancel. One of these are going to cancel. I'm going to substitute frictional force with mu times m times g. And then I'm left with kmr times alpha. I can further do some cancellations by getting rid of those two. And I get mu g over kr is equal to the angular acceleration. Again, all of these things are constant, so I can plug it into my kinematic equation for angular velocity and get my angular velocity as a function of time is equal to my initial angular velocity, which is 0 in this case, plus the acceleration times the time, which is going to be mu times g, k over r times t. So now that I have two expressions, one for the angular velocity, and I have this one for the linear velocity, all I have to do is set them equal to each other and multiply it times r, and I can solve for the time. So let's do that real quick. Get my eraser out here. Clean this up. So I want to say v equals to r omega. So I'm going to have v naught minus mu g times t is equal to r times my angular velocity equation that I just solved for over there, which is mu times g, k over r times t. Just like that. So this is my velocity, there's my radius, and there's my expression for angular velocity. So now we're going to do some cancellations here. V naught minus mu g times t. Multiply the r through, and I get mu g k times t. And now I'm just going to combine like terms and solve for t. So I get v naught is equal to mu g over k plus mu g whole thing times t. Looks like we can factor out a mu gt when I can bring that all over. So I get mu g 1 over k plus 1 times t is equal to v naught. And then we can see that we can just kind of bring all this stuff over. You can simplify this fraction. And from there, I think it's fairly straightforward that you can solve for this value of time pretty easily. And once you solve for that value of time, now you can go back and use your kinematic equations again to get your expression for the distance that it travels. So if I want to get distance, I can use a variety of kinematic equations. I could use this one right here, v naught t plus 1/2 at squared, because I've already got t, I got the t, I've already solved for a. That's one that you could use. You could certainly use this one too, since it's constant acceleration over 2 times t. There's another one that you could use to solve for that. So either one of these are going to work, as well as their rotational analogs as well. So, and you're also welcome to just take the integral and do that from 0 to t of your velocity versus time function as well. That's certainly all going to work to get your how far does it travel. So hopefully, sorry if my board got a little out of the way, this helps a little bit with the rolling with and without slipping.